Hello everyone, my name is Marcin. I am a tech lead of the autoscaling team at Google.
And I'm Maciek. I'm a software engineer at the autoscaling team at Google.
And today we would like you to give a deep dive into the blue sea of Kubernetes autoscaling. On the SIG introduction 2 days ago, we discussed that what autoscaling really is, what you can use to scale your application, and more specifically for application autoscaling, we mentioned about 2 options that you may use. The first option was horizontal scaling. In horizontal scaling, you change the number of your application replicas based on the traffic. When the traffic increases, you add some instances, and then when the traffic decreases, you remove them. Of course, you don't want to remove and add these instances manually. For that, we have a nice feature in Kubernetes called Horizontal Pod Autoscaler that is built in the core of our system. Horizontal Pod Autoscaler was covered in details on 2 talks yesterday, so I will not spend more time on it. The other option is to scale your application vertically. With vertical autoscaling, you increase or decrease the size of instances based on the current or past load. For quite a long time, there was no automatic support for this type of activity in Kubernetes. However, this spring, we managed to launch an alpha version of Vertical Pod Autoscaler, which is hoped to do the size setting automatically for you. Vertical Pod Autoscaler is not only about the reaction to the changes in load. One of the reasons why we started this project was that many users had no idea how to set their pod and container sizes right. They didn't set them at all, or they set them too small, or too big, or only partially. Vertical Pod Autoscaler is hoped to help in this case as well. To explain how Vertical Pod Autoscaler does its jobs, let's start with the API. As the VPA is in alpha, the API itself is currently available as custom resource definition. This means that it may change a little bit in the future. This also means that we need your feedback to make it great. So if you have any questions, comments, concerns on nice idea, please reach to us at the end of the presentation. At the very top level of Vertical Pod Autoscaler looks exactly as any other object in Kubernetes. There is a type, there is a name, and this Vertical Pod Autoscaler belongs to some namespace. It can have some annotations. More importantly, it contains specification and status, which I will cover right now. Let's start with the specification. In specification, we have 3 values. The first one is the selector. With it, you can tell Vertical Pod Autoscaler which pods you would like to autoscale. Containers with the same name in this pod selected with the selector will be considered as equivalent and will receive the same recommendations. The next item is the update policy. It tells what exactly you would like Vertical Pod Autoscaler to do. If you would like it to only give you recommendations and not update anything, you can set it to off. If you want it to update the recommendations only when the pods are created, you can set it to initial. And if you want to trust it to the end and turn on Vertical Pod Autoscaler at full speed, you can set it into the auto mode. In this mode, a Vertical Pod Autoscaler will apply its recommendation both to the newly created pods as well as to the pods that are currently existing in the cluster. The third element in the specification allows you to decide which containers in your pods you would like to autoscale. For these containers, which are specified by the name, you can specify the minimum and maximum amount of these resources you would like them to give. You can also put a wildcard, an asterisk in the name, and then have everything in your pods autoscaled. In such a case, you may also want to exclude some of these containers from autoscaling. To do it, you can specify the mode to off, and then these containers that you explicitly named will not be autoscaled at all. Okay, So we know what can vertical pod autoscaler do for you. Now this is the time to show how it presents its status. Again, we have 3 fields here. The first one is trivial. It says when vertical pod autoscaler updated its recommendation for the last time. The second one tells us whether all the components of vertical pod autoscaler work correctly or not, if there are any problems. And the third field contains the list of vertical pod autoscaler recommendations. The recommendation structure obviously contains the container name. However, the 3 remaining elements are a little bit more interesting. The first one is the target. This is the set of resources that vertical pod autoscaler will set on your pods. The remaining 2 are used to determine whether pods that don't necessarily have the exact target resources set are okay or not. If the pods are beyond this min and max range, they are the subject for the update. Okay, so hopefully everyone now understands the API. Let's take a look. How does it work in practice? Probably the most tricky part of the design is how we update pod requests. As you may know, deployments, for example, contain the history of all changes that were made to them. So, if you update the deployment and you set new requests on them, it is also written to the history. It may take a while until vertical pod autoscalers gets a good grasp on the right pod sizes in your deployment. And probably you don't want these changes to pollute your history. For that reason, we don't change the deployment definition while we apply the recommendations. We use something slightly different. Instead of overriding pod request, instead of setting pod requests in deployment, we override them during the admission phase. Whenever a new object is created in Kubernetes, it goes through a chain of admission plugins. These admission plugins check whether the object can be created at all and possibly apply some small changes to them. The same applies to the pods. When a pod is created, it's checked, and since 1.9 version, it can also be a subject of an external admission plugin. We use this technology in vertical pod autoscaler. So when we create a pod, it goes through admission plugin chain, and it also goes to our plugin. In this plugin, we check what are the currently configured vertical pod autoscalers, what are their recommendations, and if the new pod is the subject of some of these vertical pod autoscalers, we update its request, and then let the pod go through the rest of the chain. Calculation of the recommendation is an important part of the vertical pod autoscaler. Recommendations are calculated based on the observed real-world usage. For vertical pod autoscaler component periodically ask the metric server, formerly Hipster, for the current use of the containers. It also monitors the current set of vertical pod autoscaler objects, and based on that, it calculates what the sizes of the containers should be, and put this recommendation to VPA status field. If you allow vertical pod autoscaler to go in the full automatic mode, it will try to update the existing pods. Currently, the only way to update an existing pod is to shoot it down and kill it. So, vertical pod autoscaler constantly analyzes both the set of pods and the set of vertical pod autoscaler, and if any pod has size outside of this min and max boundary, it is killed by the updater. We do killing one by one, so eventually all of the pods that are outside of the recommended values will be updated by the admission plugins. That's all for the VPA. You can find more information on how to install and use it in our GitHub repository. And If you try it, please let us know whether you liked it, what are your ideas for the improvements. And now it's the time for the second part of the presentation, the one about Cluster Autoscaler. Can we ask questions at the end? Thank you.
Right, so Marcin told you all about pod autoscaling, and I'm going to cover node autoscaling. So basically making sure that when you autoscale your pods, there is still a place to run them in the cluster, and if you scale them down, you can actually remove the VMs so you then don't pay for them. And for that, we have a Kubernetes component called Cluster Autoscaler. It's in GA since 1.8. And out of the box, we support 3 cloud providers. So that would be Google Cloud Platform, both GKE and self-hosted clusters, Azure and AWS. I know there are also some folks who have their own forks of Cluster Autoscaler and implementation for other cloud providers, but I don't know the complete list. Right, so let's see how it works. And to actually cover how Cluster Autoscaler works, we have to take a step back and talk a bit about the Kubernetes scheduler. How scheduler does, and this is a very high-level overview, is it has 2 things really, predicate functions and priority functions. So predicate functions check if a given pod could be scheduled on a given node. So this is stuff like, do we have enough resources, CPU, memory, and so on to run a given pod on a given node? So if any of those predicates are not true, we just simply cannot schedule a pod on this node. So this is basically the filtering step. And once we do that, we actually have a bunch of nodes that could potentially host our pod, and we need to choose one of them. And this is where priorities come in. Those are basically functions that give a number of how good would it be to put this pod on this node. And they cover things like spreading pods in a single deployment among many nodes, or preferred during scheduling anti-affinity and affinity, like this sort of things. And then the final decision is just a linear combination of the scores from the different priorities. And what we care about in Cluster Autoscaler is predicates. We want to make sure that, thanks for that, mate. If you wonder, that's his computer. I wanted to tell you, yes, that we have some predicates for stuff like basically checking that we have enough resources on the node to run our pods, or there is a predicate that checks if there are taints and if the pod tolerates those taints, if the volumes are in the right zone, this sort of thing. I'm not actually going to list all of them. There is, I think, slightly less than 20. And we need to know about, like, each of them is enough, all of them must pass for a pod to schedule on a given node. And so when the Cluster Autoscaler adds a node, we need to make sure all of those would be true, so they're actually helping the pending pods. We didn't really want to re-implement all of those predicates, all of this logic, because that's a lot of logic. We would probably get it wrong. And new predicates are constantly added, the old ones are changed. So what we're doing is we literally just import the predicate code from the scheduler and bake it into our binary. That's how Cluster Autoscaler works on some very high level. We simulate what would scheduler do if the cluster shape was different. And so that was sort of the first concept we have to cover to prepare to talk about Cluster Autoscaler really. The other concept is node groups. And a node group is a set of identical nodes that can be resized. So on AWS, that would be Autoscaling Group, ASG. On Google Cloud Platform, it's Managed Instance Group, or MIG. And the important point here is that nodes in a single node group must be identical for all purposes that are relevant for scheduling. So we don't support things like multi-zone ASGs. But we support autoscaling multiple node groups. So what we're just recommending is create a separate ASG or a separate MIG in each zone, and then that will work just fine. Right. So now that we have those concepts that I will use a lot during talking about Cluster Autoscaler, let's see what cluster autoscaler does. It doesn't look at any metrics. It doesn't look at CPU usage, the actual CPU usage, because scheduler doesn't look at it. Just because we have a lot of spare CPU in our cluster will not help us if the scheduler will not schedule pods on the nodes that has this CPU. And also, just because the nodes are basically burning hot because you set the request too low, the scheduler can still put pods there, so we'll not react to that. So what we look for are pods that were marked by scheduler as unschedulable. So basically, the scheduler said, oh yeah, that guy do not fit in the cluster. So we try to fix that. And yeah, let's cover quickly how we do this. And unfortunately, this is fairly complex. But let's try to go through it pretty quickly. So basically, cluster autoscaler runs a loop every 10 seconds by default. And what it does during this loop is, first of all, it monitors the health of the cluster. We monitor the health of both cluster as a whole and different node groups. Pretty often, there are some problems where we try to scale up, but the node doesn't actually manage to boot. Or there are a lot of unhealthy nodes. Maybe there is some network issue. What we don't want to be doing is just keep adding nodes in this sort of situation, because those are still VMs on the cloud provider that you pay for. So we try to figure out if the cluster is healthy, and if it isn't, what we can do about it. If there is just a single node that failed to boot up or is unhealthy, we may try to recreate it. We'll just delete it and create a new one. So cluster autoscaler has some limited auto-healing capabilities. But if we figure out that basically everything is broken, at some point cluster autoscaler will just give up to avoid creating an even bigger mess. So that's sort of high-level overview of this part of the logic. And once we know that the cluster is in a healthy shape, we will look for the unschedulable pods, the pods that failed to schedule. We do some heuristic to filter out those pods that can actually be scheduled, but maybe weren't scheduled yet, and so on. So we try to avoid races with scheduler. And once we have them, the real autoscaling starts up, and that's where it gets complex. So what we try to do is we have this set of node groups that we're autoscaling, and then we have a set of pods that need help. So for each node group, we create a template node. It's basically a node object in cluster autoscaler memory, and we try to fit pods on this node to see which pods could possibly be helped by scaling up a given node group. And this is where we use the scheduler code, because we actually don't have the scheduling logic as something we know about in a cluster autoscaler. We just import it as a black box thing. Just give it a node object, a bunch of pods, see what happens. Right. So once we know that, we have basically a set of, we have a node group and a set of pods that could possibly fit on an empty node in this node group. So we know we could autoscale, add some nodes to this node group, and that will help these pods. But we don't know how many nodes we actually need. So we run some basically greedy bin packing algorithm with a bunch of heuristics on top to figure out how many nodes we need. We know that each of the pods would fit on an empty node, and we just try to bin pack by adding new nodes until we get all the pods scheduled in our simulation. And we do that for every node group. So I guess the point I'm trying to make here is we're doing what the scheduler does, but we do it a lot more. So we have a constant battle with performance whenever new features come to scheduler. And once we have all that information, we basically have a set of options. And the option consists of a node group, consists of a set of pods, and the number of nodes. And that basically means if we add 2 nodes to this node group, we will help this set of pods. If we add 5 nodes to this other node group, we will help this other set of pods, and so on. So now we need to make a decision which of those options we want to choose. And this is basically the most, I guess, pluggable part of cluster autoscaler. We have a bunch of different heuristics here. Those are called expanders. You can actually choose them with a flag. You're free to implement your own one. I think the best one that we like the most is pricing. scheduler, pricing expander, which basically tries to optimize long-term cost of your cluster. But unfortunately, that's only available for GCP now. And the other expanders would be much simpler heuristic, maybe like least waste, which is just waste the least amount of resources here and now, just sum up CPU and memory that is unused after scale up. And we also have a random one, but I do not recommend using that. And it's pretty easy to actually write one of those. And this is the whole scale up. But we still have to cover the scale down. Fortunately, that's going to be faster. Basically, to scale down, what we do is just we look for nodes that are unneeded, the nodes that are either completely empty or underutilized. And the node is unneeded. Well, I mean, it can be completely empty. That's easy. But if there are some pods, we just apply a set of criteria to the node to see if it's unneeded. It boils down really to it has low resource utilization. And we think all the pods there are safe to move somewhere else in the cluster. So we will not delete a node just because it has low utilization, because maybe you have 5 nodes that are 100% used, and then one node that is like 5% used. If we delete that, you end up with this 5% that have nowhere to go. So basically for each pod, once again, we use scheduler code, and we try to figure out if it could be scheduled on any of other nodes. And then there are some pods we don't like to restart because maybe they have local storage, so there would be some state that you would lose. We also don't restart kube system pods because we really don't want to restart stuff like DNS or Hipster, because this will cause potentially disruptions to your service. And finally, we let our users opt out of basically just say, add a label, actually it's an annotation, add an annotation to the pod saying, oh, this pod cannot be evicted. Or add a pod disruption budget saying, oh, only one of those can not running at a given time, so we will respect that. And if all of those conditions are true, we basically say the node is unneeded. And even node is continuously unneeded for 10 minutes by default. You can change that with flags. We will delete it. And that's basically a very high overview of how cluster autoscaler works. And I feel like that was very quick for a quite complex logic. And there are actually a lot of misconceptions. So I tried to put the most common misconceptions as a form of a summary. So this is what cluster autoscaler, and by the way, CA is how we usually abbreviate that, does. It looks at the state of the cluster, which really means nodes and pods. It looks for pending pods. This is actually the signal that we use. We simulate the scheduler, and we, I actually missed that part, so it's good I have summary. The way we actually do things is we resize node groups. So we are basically telling this node group, this cloud provider underlying concept, to change the site. We're actually not creating node objects. We're not configuring nodes, creating them. All we do is just call an API that says, for this node group, please add 2 more nodes or remove this node. This is all we do. And that's actually also on this other slide, which says what cluster autoscaler doesn't do, and a lot of people think it does it. As I said, we don't do anything with nodes other than drain them before deletion. We don't put any labels, any tags. We don't configure them in any way. We don't look at actual resource usage. All we operate on is pod requests, just as scheduler. And because of how we import scheduler code, and we actually need it baked into our binary, we do not support any form of custom scheduling, right? If you write your own scheduler, that's not supported. If you use any scheduler extender, any webhooks, any basically customization mechanism provided by SIG scheduling, we have no way of supporting this. And we don't do any predictive autoscaling. What I described is just purely reactive. We see a pod is pending, it cannot be scheduled, we fix that. We do not try to predict that, at least for now. And that's basically my quick overview of how cluster autoscaler works. And let's quickly try to cover what you can do if it doesn't work, which usually how it looks like is you have this pending pod, and well, it's like there is no new nodes coming up. Cluster Autoscaler is not working. It's not scaling up. Why could that be? So the first thing to look at is the Cluster Autoscaler status config map. We write this on every loop, and this is basically cluster status as perceived by Cluster Autoscaler. And basically, there is going to be a cluster-wide status, so the status of whole cluster and the status of each node group. So if a node group is, for example, unhealthy, we will not scale it up, and a node group will be unhealthy if too many nodes are broken. If 80% of nodes are broken, we think the whole thing is broken, we will not touch it. Maybe you can see the scale-up status, and if it says in progress, that means we actually already created a VM, it's just putting up, and we cannot really do anything about it other than wait. If it says back off, that means we had a scale-up on this group that failed recently, and we put it in exponential backoff to avoid thrashing. So in general, this is the first thing to look at. And if you ever create an issue against Autoscaler repo, please include that. That's very useful. The other thing is events. We actually write a lot of events. First of all, whenever we do anything, whenever we scale up node group or scale it down, we will write an event. We put events on pods saying, this pod has triggered scale up. This scale up was because of this pod. Or we put an event saying, this pod didn't trigger scale up. We noticed it's pending. We have not found any possible way to scale up your cluster that would actually help this pod. So, I mean, there is nothing we can do. We just put an event to let you know. And I don't think I have a slide for that, but we also have a Prometheus metrics endpoint. So that is also potentially useful for monitoring. And we put the metrics both about cluster autoscaler status, but also about basically cluster status as observed by cluster autoscaler. So how many nodes we think are unneeded, how many pending pods you have, how many pods we have evicted during scale downs, and so on and so forth. And yes, for more info, the cluster autoscaler lives in the same repository as VPA. We actually have a very large FAQ file, which we have built over the years, basically now, and it covers how to do a lot of specific configurations, how to set up specific things that you may need, and also it gives some overview over how this whole thing works. Other than that, this is a SIG talk. So we have SIG meetings at 4 p.m. UTC on Mondays. Please join us. It's not very crowded. You will clearly have a chance to say something. We're pretty active on the SIG Autoscaling Slack channel. I try to respond like within a day at most. And that's it. Thank you. Right. Do you have any questions?
Thanks. Just had a quick question about the vertical pod autoscaler. Does it keep track of the set of pods selected by a label selector in like per VPA object? So if I've got a set of pods that meets a vertical pod autoscaler CID, does it keep track of like the recommendation for those across pods across time? So if I've got like a constant stream of pods coming in, are they going to get a value that's based on the previous history of all of the pods?
Yes.
Yep. Okay. Thanks.
So my question is about node autoscaler. You are speaking about autoscaling group of nodes. Is there possibility to distinguish nodes with different groups, for example, with different resources? So when I need more CPU, I will increase the number of nodes using CPU. When I need something more from GPU, I will spawn only, rescale group of hardware which has access to GPU or SRIOV interfaces when I'm lacking them on the current point of time. Is there a possibility to operate on different groups in the same time?
Yes.
Based
so
on labels, for example.
can I take this?
That's true.
So yes, we support having multiple node groups at the same time. I mentioned quickly the expander, which is like if you can, like it's basically think for choosing which node group to expand, which sort of like you can. What I'm trying to say is you can have multiple node groups, and it's part of cloud provider specific implementation to implement a function that actually for each node tells us which node group it belongs to. So basically, if you were to implement your own cloud provider, you would have to write this function. And for the cloud providers we support, we have the implementation, obviously. So for each node group, you can tell in which for each node we can tell in which node group it is, and the whole scale-up logic is performed for each node group. We basically see what we can do for different pods, and then we just choose one of those options. And if you would have one pod that maybe requires GPU and can only go to the node group with GPU, and the other, but maybe this node group is tainted, so other pods cannot go there, we will just trigger two separate scale-ups, one for the GPU group and then one for the other pods. And those are just sort of two separate scale-ups. Yes.
So you optimize.
There was a lady with a question first.
Okay, my question about vertical pod autoscaler. As you mentioned, you said that you are not changing requests. I mean limits requests, right?
Sorry? Once more, please.
You are not during this changing during scaling. You are not changing requests, right?
We are not changing requests in the deployment object.
Okay.
So we don't change the request in the template. However, once the pod is created based on this template, we update it during the admission phase.
Okay, and as I understand, scheduler works based on requests, right?
Yes, that's correct.
So basically, when next pod will be scaled, right? It can't rely on sum of requests, which is currently calculated for example, some specific node, right? So how you deal with that? So it can be a situation when actually working load on this node's much higher, but schedule decided that it enough that new pod can be scheduled in this node.
Yes, so once the pod is updated, it can go to a different node, and it's a perfectly valid situation. So scheduler tries to pick the best node to run a pod with specific requirements. So for example, it may land on the exactly same node as it is used to be. However, it may also land on some other node if the other node is simply better according to the scheduler to host this pod. Sometime in the future, we hope to have in-place upgrades. So we will first try to update the pod request without actually killing it. However, it requires a lot of stuff in Node and scheduler code base, and we are in the process of dealing with it. So stay tuned.
Do you mean like pod admission controller works before scheduler?
Sorry, there is a queue of people asking questions.
No, but that's a question for clarification. Yes, our admission plugin actually updates the pod request on admission before the scheduler ever sees the pod. So it only sees updated pod. It never sees the original one.
Any other clarification questions?
Keep moving. Let's say there's a case when you have, let's say, Postgres with master slave, and how to prevent master to be killed instead of slave. Is it possible?
In which autoscaler? Just to clarify. Okay, so there is something called pod disruption budget, and you may say that you don't want some set of pods to be killed, and you may designate the master to have allowed disruptions equal to 0.
Or give it a do not evict annotation.
I just want to ask, you will optimize across node groups, is that correct? When you're scaling up, when he was talking about node groups, when you take a particular pod, you will sort of do the optimize across the node groups, or you check on a per node group basis, or across all node groups? So
in a single loop, we will scale up at most, on a single loop of cluster autoscaler, we will scale up at most one node group. But if you have pods that like better fit different groups,
Yes.
we can just do it one by one. We have a loop every 10 seconds. So if you have a GPU pod, it will go in one iteration. We will scale up the GPU node group. If you have a non-GPU pods, in the next iteration, we will do a scale up for those.
But could a pod basically sort of be scheduled on either one of the node groups? And is that, I mean, how do you know which one's ideal for them? Is that a possibility?
Right. So we cannot do this sort of a per pod, like everything calculation, because it gets too computationally expensive.
Okay.
So what we do is basically we use a greedy approach here. For each node group, we see the maximum number of pods that we can fit into this node group as one option, and then we pick the best option. So hopefully, if you have a very ineffective way of fitting pods, like this option will not be very attractive, and we'll first do a different scale up, and then on the next loop, those pods that were like that didn't make sense has already gone somewhere else.
Okay. All right. Thank you.
One clarification here. So usually pods don't come at random. So at 1 10-second slot, you create one deployment and you give us the set of equally looking pod. Slightly later, something else kicks in and creates another set of equally looking pods. So in most of the cases, Cluster Autoscaler works on exactly same set of pods. So they are not mixed. However, we support cases when they are slightly mixed.
I have a question on the Cluster Autoscaler. Is if there's ever any way that you can get the cluster to autoscale based on the actual utilization of the node. So if you have full CPU usage, but you set a big difference between your requests and your limits, so you can still technically schedule within the request range, but actually the node is under CPU pressure.
So it's the task of horizontal and vertical pod autoscaler to make sure that your pods are not burning hot. So horizontal pod autoscaler, based on your traffic, may spin up new instances, and these instances may not have a good place to go. So, and in that case, cluster autoscaler will kick in. The similar situation, vertical pod autoscaler may see that you are using too many resources on your pod, and these resources needs to be increased in order to reflect the reality. And this pod cannot go anywhere else, and then cluster autoscaler will kick in. Last question.
So how do you see the vertical autoscaler being used in conjunction with the vertical autoscaler?
Vertical autoscaler with conjunction with horizontal pod autoscaler?
Yes.
Two together?
Yeah.
Okay.
So to be more specific, for example, if my application actually has grown and needs more resources, I would like it to grow vertically up, while if I have a surge of requests, I would want it to go horizontally. Sorry.
Okay, I understood. So mixing horizontal and vertical pod autoscaler is not fully supported. So both of these autoscaler are for similar purpose. They want to deal with a situation when your pods are overloaded. They don't talk to each other, so they can make this similar decision at the same time. For example, horizontal pod autoscaler may spin up a couple of new instances, and vertical pod autoscaler at the same time add you a couple bigger pods. In the situation, you will get too much capacity, and then it will have to go back. So combining CPU-based autoscaling and CPU-based vertical pod autoscaling is not necessarily the best idea. A slightly better idea is to use custom metrics in horizontal pod autoscaler. In such a way, you have separated a little bit the CPU load from horizontal pod autoscaler, from CPU load taken into account in vertical pod autoscaler. However, it needs to be thoroughly tested and validated on per case basis.
Thank you.
Okay?
Okay, thank you.
Thank you, and have a safe trip back home.